Dear friends, hearty welcome to the online problem solving session series organized by Maths Aspirants groups. Today is the third session on the topic ordinary differential equation, and we are having Dr. Himanshu as the resource person for the session. Dr. Himanshu recently awarded PhD from IIT Delhi and now working as a postdoc fellow there. Without any delay, I welcome everyone to this program. And I would like to express my thanks to Dr. Himanshu for being with Math Aspirants. Once again, I welcome everyone to this event. Welcome, Himanshu.
Thank you, sir. Thank you, Vinod, sir, for inviting me for this session. So, discussing with the students is really a nice opportunity for me as well. So, this is the third session. So, let me share my screen. So, in this session, we discuss two things. Generally, the one thing is system of linear differential equation, and second one we see the questions on boundary value problem. So again, as we did it in last two sessions as well, so I provide in this session the theory part. So before having some questions, so we just recap it with the theory part and then we see some questions. So since we are just 2 days before, so I have added almost all the results that are required for system of linear differential equation and boundary value problem. So maybe you can use it later as a revision part, this PPT as well. So I will share it with this at the end of lecture. So let's start it. So as you know that a system of differential equation is a collection of two or more differential equations involving the independent variable and dependent variable. So these systems occurs in many branches of the science. So maybe you have seen in electrical circuits and the dynamical systems. So let me define it more generally. So let's say if we have n functions of t and each function is showing the rate of change with respect to the variable t, x1, x2, and say we have n variable till xn, then before solving this, we have some notation for this. So let's just write it in this form, and we can write it in the matrix representation form in this way. I hope this everyone knows this representation of a system of linear differential equations. So generally this type of representation is more seen during the questions. So we have our system of differential equation defined by x dash t equals to at xt plus bt, where at is the coefficient matrix of the variable xi and bt is the right hand side. So whenever bt, the right hand side is 0, then our system is a homogeneous system. And when bt is non-zero, then it is a non-homogeneous system. So here we have an example. Let's say our system is defined by x1 dash equals to 2x1 plus x2, x2 dash plus x1 plus 2x2. Then how we will write it in the matrix form? So we just take the coefficients out in the given system and write it like this. So here I have taken 2 and 1 out. So how I have done this? So this is done like this: 2, 1, 1, 2, and then x1, x2. So this is my vector x, and my x dash is x1 dash, x2 dash. So this is the vector x dash. I hope this everyone knows. If in case someone does not know, so I have written it here. So now similarly we have non-homogeneous system and bt is non-zero. So this is an example of the non-homogeneous system. So how we will write it in the matrix representation form? The matrix representation form of the non-homogeneous system is defined in this way. So we just take the e raised to the power t right hand side, since this is a function which is free from x1 and x2. So we can write it in this form. So I hope till now this is clear. So these are the basic definitions. Similarly, as we have done in the second order or higher order differential equation, so uh, whenever our matrix AT and BT are continuous, our this means all the coefficients in AT are continuous. Whenever I am saying a matrix is continuous, okay. Then the initial value problem has a unique solution on I whenever it satisfies this condition, which is AT and BT are continuous on I. Similarly, if we have some solution, then the linear combination is also a solution for the homogeneous case. How we can solve this uh, system of differential equation? So solving system of differential equation is same as solving the linear system. Like we have solved the one variable case that, for example, if I have this equation y, let's say y dash plus px, let me just write it more better way. Y dash equals to say some c time of x or c time of y. Then solving this system is same as solving this system. So the proof is quite easy, so I'm not going into that. So here is one example that I have written here. So one way of solving the system of differential equation is through eigenvalues and eigenvectors. This we will see in the upcoming slides. And the another way is, for example, we have the system in the matrix form. You just open it out, simplify the system. So what we are doing it here. So let's say I have 1, 0, 0, minus 2, x1, x2 here. Just open this matrix form and compare the terms. We have our differential equation this and solve this differential equation. Then solving first this system, solving solving this another system, we get this solution. Since this my system is independent of x2, so we can solve it separately. Similarly, for x2, we can solve it separately and we can get one solution. But not always we can solve it like this. So we have another methods as well that we will see in the upcoming slides. There is one more thing that is common, like you can change any differential equation into system of differential equation and vice versa as well. So let's see how we can do that. Okay, maybe I think I have added this slide in between that. So before, okay, so let's see this first. So let's say we have our system in two variables, x and y, and these x and y are dependent on my variable t. Then we can eliminate x and y, like we are solving the system of equations and have the value of y in terms of t only. So maybe I can tell you with the help of an example. Let's say we have dx by dt like this, dy by dt like this. So the one way is you just differentiate it. You just take any of the equation. Let's say you are taking this equation, differentiate it with respect to t. So what we will have it here? So we will have it here as d square x by dt square minus 3 dx by dt plus, since y depends on t, we have dy by dt equals to e raised to the power minus 2t. So just substitute the value of dy by dt from here in this. You have an equation in one variable x, which is depending on t. So this is up to you how you can do that. The another way is just write it in the operator form and then just do the elimination. So once you eliminate one variable, you get the differential equation in one variable case. Now, vice versa, if we want to see it, then how we can do that? So let's say we have our nth order differential equation. So this is my nth order linear differential equation. So we introduce the new variables. So we introduce the variable in the form x1 equals to x, x2 equals to dx by dt, and xn equals to dn minus 1 x dt raised to the power n. So this is the n minus 1th order. So now how we will convert that? So we use this, and we know that the relation, once we take the derivative of my last function, so it will be d of xn over dt, which is equivalent to dn x over dt n minus 1. Sorry, it's dtn. So the value of our this derivative, we can obtain it from here. So just take this term here on my right hand side, and we know what this function is. So maybe we can see through an example. So here we have x1 equals to x, x2 equals to dx by dt, x3 equals to d2x over d2 square. So once we differentiate it, then our left hand side is our differentiation function, which is x1 dash, x2 dash, and x3 dash. And my right hand side, this will become this form, where this matrix is a companion matrix. I hope you are aware of the companion matrix. So there is a one-to-one relation. So if we have a non-homogeneous system here, then we will obtain a non-homogeneous system of differential equation. And if my ft is 0, that means if my nth order linear differential equation is homogeneous, then my system of differential equation is also homogeneous. I hope this everyone knows. So now how we can solve it? So as we have seen in second order differential equation, we can solve our system through variation of parameter. So here I have just assumed a function for particular value xt and ut. So the substitute this value of where xt is the solution of my main function. So substitute this value in the differential equation, and we can see that this is my formula. So before going further, if anyone has doubt, then please ask. Okay, great then. So here is one example of the variation of parameters. Let's say this is my differential equation, and this is the solution. You can verify it, and just take the x inverse of this. Why x inverse exists? Because our functions, these are two linearly independent eigenvectors. That's why their inverse exists. And after solving this, we can find the particular value. So maybe this section that I have added, we can study through an example. Now, what about if we have, let's say I have this system. So in this system, in this matrix form, we know that there is one eigenvalue, which is 2 and 2 of multiplicity 2. And there is only one eigenvector, since we don't have two eigenvectors, and for solution we need two eigenvectors. So in that case, we will find the generalized eigenvector. Let's say if V1 is an eigenvector of matrix 2, 1, 0, 2, then we find its second eigenvector as A V2 equals to V1. So this is called a generalized eigenvector. I hope this thing also everyone knows. So using that, we can find our solution. Now let me explain the main definition here that is more useful through an exam point of view. So what are critical points? So now the upcoming slides, whatever the result I say, it will be very important. So let's say we have the system dx by dt equals to pxy, dy by dt equals to qxy. Then x naught comma y naught is a critical point if and only if it satisfies p and q. So in most of the questions during the exam, the critical points is known, and we have to find the behavior of our differential system on these critical points. So in case if critical points are not known, then we can find the critical points by finding the zeros of P and Q. So through these critical points, we will study the behavior of our differential system. Now we define the Jacobian matrix. So we know that Jacobian matrix is defined by for 2 cross 2 system, it will be del P over del X, del P over del Y, del Q over del X, and del Q over del Y. Now we study the behavior of our critical point of this matrix J. If the system is a linear system, in that case, one can check that 0,0 is always a critical point here. Right? You can see that once you substitute 0, 0 here, this is 0, this is also 0, right? Now we can study the behavior of this. How we'll study the behavior of this? We find its eigenvalues, and depending on the eigenvalues of this matrix or this matrix, what we can say about their behavior. So generally we are worrying about three things. So when our critical point is stable, when it is asymptotically stable, and when it is unstable. So a point is stable if for every epsilon greater than 0, there exists delta greater than 0, such that whenever my vector points are close, then my function is also closed for all t greater than equals to t. It is asymptotically stable. So whenever we take our function which goes to infinity, whenever my function t goes to infinity, then my function is converging to 0, 0. If it is not the case, then we say our critical point behaves unstably. So maybe this we can understand through an example. So through an example, this will be more clear. So here I have just given a relation on the lambda 1 and lambda 2. Now, what are phase portrait diagrams? So a phase portrait diagram is a geometric representation of solution curves in the xy plane. So here I have given the behavior. So I will tell you what are the conditions that we have on eigenvalues, and our phase portrait behaves in this form. So before saying it, so what kind of phase portrait diagrams we have? So one, this is center, this is stable node. Since you can see that this is stable because it is converging to 0, 0 whenever my function is going to infinity. So this is a stable spiral code. So here again, it is converging to my critical point here. Here, this is unstable because whenever my function is going infinity, then my curve, my graph is going very far away from the critical point. Now it is unstable again here. Why it is unstable? Again, it is going outside to my critical point. And why it is a saddle point? Again, whenever my t tends to infinity, then in one direction it go up and it go down. So this is what I have written here, the thing that I have said. Now let's have the condition on eigenvalues, and through eigenvalues what we can say about the behavior. So once my lambda1 and lambda2 are eigenvalues of A, if my eigenvalues are of different sign, then it will always be a saddle point. If my both eigenvalues are negative, then it will be a stable node. If my both eigenvalues are positive, then it will be an unstable node. I hope this everyone knows. If no, then I can explain this it in more detail. If you want it, then please tell me. So I will explain this thing in a more detail. So I'm just going fast because I'm believing that you guys have already studied it. Once, if my eigenvalues are complex, then it is either spiral or center. If it's real part of the complex value is negative, then it is a spiral sink. If my real part is positive, then it will be a spiral source. And if alpha is 0, that means real part is 0, then it will be a center. Why I'm doing this? So I'm just giving you an idea. So it will be my function e raised to the power alpha plus iota beta. This is same as e raised to the power alpha cos beta plus iota sin beta. So just substitute the value of alpha and beta here. If alpha is negative, whenever my function going to infinity, then it will always approaches 0. Since this is a bounded function, so this will always goes to a 0. When this my function, when this alpha is positive, then when t tends to infinity, then it will also diverge. So it will become unbounded. When my alpha is 0, then it will be a center because it is revolving around a single point. Okay, great then. So this
Sir,
is,
1 minute. Sir, excuse me, sir.
sorry,
Sir, could you show the previous slide, sir?
which one?
Previous
This
one, sir.
one?
Previous one. Yes, sir. 1 minute, sir. Thank you, sir. Thank you, sir. Thank you so much, sir.
Okay, okay. So this is the summary that I have written here. So you can use this as a reference. But the more thing, the important thing is like you should know how we are doing this. So that is more important. Now let's have some question, and depending on that, let's see the behavior. So this is the question that comes in the CSI and NET. So the question says that consider the system of ordinary differential equation dy by dt equals to ay, where the matrix A is given by this, and we have this initial value problem. So the question is about the functions y1 and y2. So if these are the solutions, then what we can say about them? So are they monotonically increasing or they are monotonically decreasing? If yes, then in which domain? So I wanted to try it. So try this question and tell me the answer. is how can you proceed this question? So there are two ways of doing this question. The one is you write the matrix like this: y1 dash, y2 dash equals to -1, 1, -1, 1, 0, -1, y1, y2. So just open it out, solve for y2, and then substitute the value of y2 in my first equation, and then solve for y1. So this is one way of doing it. The another way of doing it is find its eigenvalues. Here the eigenvalues are -1 and -1, and it is in a JCF form. This is the Jordan canonical form of block 2 of eigenvalue -1, right? So we required one generalized eigenvector in that. Solve that, then check the properties of y1 and y2. Is it clear how we can do this question?
Sir, found the eigenvalues and eigenvectors, sir. Afterwards, what shall we do? Don't know
Yes, sir.
about
Okay,
this.
so sorry.
I could find eigenvalues and eigenvectors, sir. Afterwards, what shall I do? I
So
don't know about. Yes, sir.
we are given this initial value condition, right?
Yes, sir.
So we can write our function yt in general form.
Sure, sir.
Okay, so let me see the solution. So this is my function yt we obtain after substituting our function. So what we have done it here more. So we write it like this: t raised to the power minus t e raised to the power minus t. So this is my y1, the first part. This is y1 and this is y2. Is this clear?
Yes, sir.
Yes. So now we have to see their property, this property.
Sure,
So
sir.
how we can check monotonic increasing or monotonic decreasing? So we will differentiate y1 and we will differentiate y2 and see the property. So my function is monotonically increasing when my y dash t is greater than 0. Whenever it is greater than 0 in some domain, for that domain, my function is increasing. Okay. So we
Yes, sir.
can
Sure,
see
sir.
that our function is monotonic decreasing for t greater than 1. So the key steps I have written it here. So the main thing that I want you to understand, that I know that you can solve the question, but later after solving the eigenvectors and eigenvalues, how you can proceed. Okay. Now let's go to the another question. So the question is about the critical point of this system. Now we have this system. Now note that we are not given any critical points. So the critical points will be the zeros of, here my pxy is minus 4x minus y, and qxy is x minus 2y. So this is a system of linear equations, right? So if we write it in the matrix form, -4, -1, 1, -2, x, y, 0, 0. So determinant of y coefficient matrix is non-zero. So we have our solution as 0, 0 is one of the solution. So in case if nothing is given, always substitute the 0, 0 in our functions P and Q. Then check the behavior at 0, 0 if it satisfies P and Q. Okay.
Yes, sir.
Now we find the eigenvalues and eigenvector of this matrix. So can you tell me the eigenvalues and eigenvectors? Okay, see, this is my matrix, right? If we do this
So
sum
minus
here, the
3.
column sum is -3. Very good. So the column sum is -3. Again here the column sum is -3. So -3 is one eigenvalue and trace is -6. Then my another eigenvalue will also be -3, right? So we have two eigenvalues which are -3. And we know that whenever both eigenvalues are negative, then the behavior is asymptotically stable node. Is this clear how I have said this? See, I have not used any, just I need my pen and paper for writing this only. Other than that, I don't need
Yes, sir.
even pen and paper for solving this question. Is this clear?
Oh, yes, sir. Very nice explanation, sir.
Great then. So here I have written the explanation. You can read that also. Now let's come back to this question, the another question. So the another question says that if we have xt and yt satisfying the system dx by dt equals to minus x plus ty, dy by dt equals to tx minus y, and if x1t, y1t and x2, y2t are two solutions satisfying our system, and we define the phi t as x1t, y2t minus x2t, y1t. Then the derivative of phi with respect to t is minus 2 phi, 2 phi, minus 5 phi. So what will be the approach here? So there is one thing that I wanted from you guys. So once I read the question, so if possible, then please just tell me one thing, how we can proceed this question. Have you seen like what kind of thing this is?
It's kind of like the determinant.
Isn't it same as this? Yes, very good. So this is same as if we have x1, say x2, y1, y2, then my determinant is x1, y2 minus x2, y1, right? So now compute the phi dash t. This is also a determinant. So what you can do this, either you take this function take this function phi t and differentiate it with respect to t. And then use this function. So my left hand side is x dash t, my right hand side is y dash t. Substitute this in this function and obtain the relation. Even you don't need the concept of differential equation. So you just, if you notice this thing that this is the determinant, then you can solve this question. Okay, so this is what I have done here. So I have differentiated it with respect to t, and using our given system, substitute it back here. We can found this relation. Minus 2 pi. Yes. Very good. Okay, then let's go to our another question. So now note that in this question, my right hand side is not linear. So the question is about the behavior of our system where the critical point is 0, 0. So how we will do that? So this is our function Pxy. This is Qxy. How we can find the behavior? We'll find its Jacobian P, Q at 0, 0, right? And we'll check its eigenvalues depending on the sign of eigenvalues. We can comment about its behavior. So idea is clear, right? Okay, so how we have done this? So we found the Jacobian at the 0, 0. So my function is this function. So now we compute the eigenvalues and eigenvectors of this matrix. Here my eigenvalues and eigenvectors are this, right? So we know that root 5 is greater than or equals to 2. Root 5 is strictly greater than 2. So my one eigenvalue is positive and another eigenvalue is negative. So the behavior is, yes, I have told you the eigenvalues. Now can you tell me the behavior of our system? Yes. Is it clear? Very nice. So we have a similar question. So our system is dx by dt equals to x into 3 minus 2x minus 2y, and dy by dt equals to y into 2 minus 2x minus 2y. And the critical point is given to us, which is 0, 2. If critical point is not given, then we can compute it by comparing it equals to 0. So we have our two system and then find the values of x and y from there. Okay, so I'm giving you the eigenvalues and eigenvectors here. So you know that we find its Jacobian at 0, 2, and we have to see the behavior of that matrix. So if my eigenvalues and eigenvectors are, sorry, if my eigenvalues are -1 and -2, so can you tell me the behavior now? Once my both eigenvalues are negative, so my function is of the form e raised to the power minus t and e raised to the power minus 2t. So whenever my t tends to infinity, it will be a converging to 0. So it will be asymptotically stable node. I hope you know the meaning of this asymptotically, right? This means whenever we are taking t tends to infinity and behavior of our system. Now let's go to the next question. So let's say we have our system dx by dt equals to ax and our x1t and x2 are two solutions, then which of the following are true? Options itself says a lot of things, right?
Option A, sir.
So how we compute the eigenvalues? Again here, column sum is 1, so one eigenvalue is 1, trace is 2, right? So we have both eigenvalues 1, 1, right? Then we can find the eigenvectors also. Here geometric multiplicity will be 1, so we have only one eigenvector, right? Which is 1, -1. So my second eigenvector will come out to be this one. And we know that these two eigenvectors are both linearly independent. So my all options A, B, C, and D are true. So very simple questions during exams will come. So it's very easy to get marks in system of differential equations. Okay. So now let's go to next question. So the next question, if we have this system of differential equation, now which of the following are true? Every solution is bounded. Every solution is periodic. There exists a bounded solution. There exists a non-periodic solution. So in this case, no much information is given to us. So we have to find the solution. How we do that? You know that if you find its characteristic equation, we have lambda square plus 1 equals to 0. Our both eigenvalues are imaginary, right? See, there is question to you guys. So how many of you will solve the system of differential equation using system of differential equation? Just by directly reading the question, you can directly tell the answers without even solving it. If you read the question carefully, then you can directly tell the answers of this question. Can anyone tell me how we can do that? So the one way of solving this is just compare the
A, B, C, sir.
coordinates. Very good. How you have done this? So it is clear from our eigenvalues that my system will have solution in terms of sine and cos, and my sine function and cos function are periodic, bounded, and it is a bounded solution. So we can say directly A, B, C options are true and option D is false. So this is what intuition I have it in my mind. Now let's go back. Now let's see this question. The question is, if we have our system y dash x equals to a by x, where my matrix coefficient matrix is -3, -1, k, -2, such that the solution tends to 0 as x tends to infinity, then what we can say about our set S, where S is the set of all values of k. I hope the question is clear to everyone.
Yes, sir.
How we can do that? What we will do in that? So our solution will tend to 0 when we have our both eigenvalues. Both eigenvalues.
Negative, sir.
Negative. Right? So what conditions on k we impose such that our eigenvalues are negative?
K is equal to 0, sir.
Yes, k equals to 0. But here see the options. So the options are, it is contained in R negative, it is dense in R negative, it is bounded above but not below, it is bounded below but not above. Okay, so let's see the solution. So this is what I have done here. So we want to be the real part of lambda to be negative in case if we have eigenvalues are imaginary. So for that we want trace of A to be less than 0 and determinant of A to be greater than 0. Right? I hope this is clear. So that gives us the condition k is greater than -6. So k is -6 to infinity. So what we can say from this? So this is the condition, k is greater than -6. So my set S is -6 to infinity, so it is bounded below but not bounded above. Is it clear? Great then. Now we have some theory on boundary value problem. So we go a little fast since we have less time. So like what are boundary value problems? So we have a differential equation and we have the conditions given on the boundary values, right? So let's say we have our system y double dash plus pxy dash plus qxy equals to fx, and we are looking the solutions on closed interval a comma b. Then we have our condition on the endpoints, which are the boundary points in real line. Okay, so the interval a comma b are where a and b are the boundary points. So these are called the boundary value problems. So now let's define it more properly. So a homogeneous boundary value problem has the form y double dash plus pxy dash plus qxy equals to 0. Again, we have right hand side 0 with the boundary condition alpha 1 y plus beta 1 y dash a, alpha 2 yb plus beta 2 y dash b equals to 0. So here one more condition is needed that I forgot to write it, which will be alpha 1 square plus beta 1 square is not equals to 0. So this alpha 1 and beta 1 both simultaneously cannot be 0. Similarly, alpha 2 and beta also together cannot be 0. And we know that yx equals to 0 will always be a solution. So we are interested in the solution which are non-trivial. So this is the motivation of having eigenvalues and eigenvectors in that. So we have a boundary value condition which is depending on the parameter lambda, which is y double dash plus lambda y equals to 0. So we are looking the non-trivial solution of this differential equation when lambda is a variable. Then what we can say that. So if I vary my lambda, then what can I say about the non-trivial solution of this system? So whenever we have non-trivial solution, that solutions are called the eigenfunctions with respect to that value of lambda. Let's say we have y double dash plus lambda y equals to 0 and the boundary conditions are given at 0 and pi. Then we are interested in non-trivial solution of our system y double dash plus lambda y. So whenever lambda is 0, then we have a trivial solution. When my lambda is less than 0, again using the boundary value problem, using this boundary condition, we can again show that my solution will be a trivial solution. So we have a non-trivial solution if and only if we have lambda is greater than 0. So I believe that this is very easy. So in this case, we have lambda equals to n square and solutions are depending on n. So the solutions are sin x. For each value of n, we have our eigenfunction sin nx. So one thing to observe here, we have countably infinite eigenvalues and countably infinite linearly independent eigenfunctions. One more thing to observe here, that our eigenfunctions sin nx in domain 0, pi have finitely many zeros. So this observation I have written in upcoming slides as well. So sometimes the questions directly comes based on these observations. Now we define what are self-adjoint. So a second order differential equation is called self-adjoint if it can be written as in this form: dy by dx of px into dy by dx plus qxy equals to 0, where px is positive and p and q are continuous functions. Why we are doing self-adjoint? We know that there is a well-known result that eigenvalues for self-adjoint metric, a self-adjoint differential equation is always real. So these are some results that all eigenvalues are reals and eigenfunctions corresponding to distinct eigenvalues are orthogonal, and we can always put our eigenvalues in an increasing sequence which is unbounded and it is going to infinity. So here is the meaning of our orthogonal functions. Now we have an example y double dash plus lambda y equals to 0, y0 equals to 0, y dash 1 equals to 0. So in most of the cases, once you solve this differential equation using this boundary value conditions, our lambda is less than, our lambda is positive, and we have our solution is bounded and periodic function. Now let's talk about more properties of regular and periodic boundary value problems. Let's say if I have a set A, which is the collection of all my eigenvalues, then as we have seen that my eigenvalues are infinite, these are countably infinite, and we can arrange it in a increasing order such that my eigenvalues are approaches to infinity whenever my n tending to infinity. And my set A is always bounded below and unbounded above. And each my set A is every element of A is isolated point and it is never dense in R. Now what we can say about least eigenvalue? There exists lambda naught belongs to R such that for all lambda greater than lambda naught, the differential equation has a non-trivial solution. And for the least eigenvalue, we don't have any solution. So we are talking about the zeros of the eigenfunctions corresponding to my least eigenvalue. So once I have a least eigenvalue, then it has no zeros, and other than my least eigenvalue, my all eigenfunctions corresponding to those eigenvalues have at least 1 zero. What we can say about the dimension of the eigenspaces? So for regular boundary value problem, the dimension of each eigenspace is always 1. And for the nth eigenvalue, the corresponding eigenfunction has exactly n minus 1 zeros within the boundaries. Also, there exists an eigenvalue lambda such that the corresponding eigenfunction changes signs in A comma B. So what we can take it that we can take any other than the least eigenvalue, take other eigenvalue that will always change the sign. For the least eigenvalue lambda naught, it don't have any solution, so it will never cross the x-axis. So we have one eigenvalue that does not change any sign in that. Similarly, there exists an eigenvalue lambda such that their kth derivative also changes the sign. So we can take the corresponding eigenfunction with respect to eigenvalue greater than k. So I hope this is clear. So few questions directly came based on this properties only. So this is what I have said about the eigenvalues, the zeros of that. Now what we can say about general theory for periodic boundary value problem. So again, let's say we have set A, then our set of eigenvalues are countably infinite. It can arrange in the increasing order, and my eigenvalues will tend to infinity whenever n tends to infinity. The dimension of eigenspace corresponding to the least eigenvalue is 1, and for other than least eigenvalue, eigenspace contains at least 2 eigenfunctions. Again, the same thing we can say about the eigenfunctions. The zero of the eigenvalues, if lambda equals to 0 is an eigenvalue and dimension of E lambda equals to 1, then this will be a least eigenvalue, right? So we don't have any other eigenvalue. I think there is some mistake here. So here I have written that there exists at least one negative eigenvalue. So in the first bullet point, when lambda is 0 and dimension of E lambda equals to 1, then there exists no negative eigenvalue. So please make a correction here. So the first bullet point, so I have written the same statement. So there is a mistake. So the mistake is in first bullet point, there exists no negative eigenvalue. Now let's see an example of periodic boundary value problem. So we have y double dash plus 2y dash minus 3y equals to 0. And we are given the boundary value conditions, y0 equals to 0, y dash 1 equals to 0. So we can solve this system, we can solve this differential equation, and we can find yx equals to 0 is only trivial solution. So in that case, we don't have any eigenvalue and we don't have any eigenfunction in this case. Now for the system, now for the differential equation, y double dash equals to 0 with respect to boundary value condition, y minus 1 equals to 0, y1 minus 2 y dash 1 equals to 0. Our system is this. So we have non-trivial solution in this case, and our function 1 and x are two solutions of this. Now let's come back to the previous year questions of boundary value problem. So now we have the differential equation minus u double dash x equals to pi square ux, where my function is defining the domain 0, 1, and we are given the boundary value conditions on 0 and 1 are 0. So what we can say about u dash square x plus pi square u square x equals to u dash 0. So which options is true? So I just want an idea how you proceed this question. So I don't want you to solve this question now since it will take time. So I just want your approach how you can proceed this question. Note that this is a differential equation where its coefficients are constants only. So we can always solve the system, right? Since it involves the integral and differential equation, so it is always best to solve this system, solve this differential equation, and then substitute in the options. Right? So find the solution here, find the solution ux, and substitute in the option and check which options are true. Okay, great then. If you don't have a doubt, let's go to the question. So we have the boundary value problem, y double dash plus lambda y equals to 0, defined on the domain 0 and 1. The boundary conditions are y0 equals to 0 and y1 equals to 0. So the question is, there exists an eigenvalue lambda for which the corresponding eigenfunction is 0, 1. So this is a self-adjoint matrix. So this is a regular boundary value problem. Is it clear? Great. So the question is, there exists. So we are not saying ki always. So we are talking about there exists, right? So this based on the properties that we have just done in the previous slides. So we know that for the least eigenvalue, my corresponding eigenfunction does not change sign, right? So option A is always true. For other than least eigenvalues, we have zeros, so it will change sign, right? So option B is true. Option C is also true, right? It is not changing sign means it is either positive or it is negative. So that's why my option A, B, C, D all are true. Again, in this question, we don't need any pen and paper. Read them. So let's go to the another question. So the eigenvalues of the Sturm-Liouville system y double dash plus lambda y equals to 0. So that y0 equals to 0 and y dash pi equals to 0. So here we are talking about the eigenvalues. So again, it is clear from the options. My lambda will be positive, right? But option A, B, C says my eigenvalue has to be positive. But since there is none of these, so we have to verify for lambda equals to 0 and lambda less than 0. So you can compute this and can find the solution. So we have to solve this differential equation using this boundary values. We can see that option B is true. I hope yes. So here this is a straightforward question. We just need to do some calculation and we can get our answer. Now it's an interesting question. So if you know the properties, you can again do this question. So the question is, consider this Sturm-Liouville problem 1 plus x square y double dash plus 2xy dash plus lambda x square y equals to 0. With y dash 1 equals to 0 and y dash 10 equals to 0, then the eigenvalue is lambda satisfied. Since it's a Sturm-Liouville problem, it's a self-adjoint differential equation, so the eigenvalues are always real. Now the question is about lambda is greater than equals to 0, lambda is less than 0, lambda is not equals to 0, and lambda is less than equals to 0. So we are talking about eigenvalues here. Again, this question is based on the properties that we have discussed. Can anyone tell me how we can do that? So how many of you think that we can solve this question? If yes, then what is your approach? Yes, anyone? Okay, then let me tell you the solution here. So again here, if you remember the properties correctly, then we know that our collection of eigenvalues, it's a unbounded set, right? So whenever my n tends to infinity, my eigenvalues are very big and big. So from that, we can say that option B and option D are false. Now let's come back to the option A and C. You can easily verify by substituting lambda equals to 0. Then we have one non-trivial solution in this case. So that discards option C as well. So our option A is true. So is it clear how we do this question? Any doubt in this question? Great. So now so here I have done this. So I think by going through option. So here I have made a mistake. So please, there is something that I have written wrong here. So option A is true in this case. Now again, this question directly based on the properties. So given this differential equation on A comma B with y equals to yb and y dash a equals to y dash b, where p of a equals to p of b and p dash q are continuous, p is positive, q is positive on a b. So these are the periodic boundary conditions. So again, this question is directly based on its properties. So we can see that the option A is true. The given problem has periodic boundary conditions. As we have seen in the properties, there exists a sequence of eigenvalues which we can arrange increasingly such that my lambda n tends to infinity. As n tends to infinity, the eigenfunctions corresponding to the some eigenvalues change sign in A comma B. This is also true if we take other than least eigenvalue, right? And the eigenspace corresponding to some eigenvalues is of dimension 2, right? This is also true, right? Other than least eigenvalue. So this is what we have done here. Is this question clear? So this is it from my side. So now, if you have any question, then please ask.
Yeah. Thank you, Himanshu, for this nice session. I'm sure that as the examination is very near, so those who are seriously preparing for CSE or NET, definitely today's session will be really helpful. Archana.
Hello, sir. I'm Archana. Sir, I have really enjoyed your class. Your explanation was clear cut. And the way you applied each question for CSI net level itself was really helpful. And as I am actually a JAM aspirant, so I don't know much about two variable differential functions, yet I was able to understand and actually solve a few of the questions. So I really enjoyed your sessions, sir. And I'm hoping you do more sessions. Yesterday, I was sitting and watching all your previous sessions you had organized for Max aspirants. So I really enjoy your teaching style and the way of your explanation. Thank you, sir.
Thank you, Archana. Yeah, Subra Kundu.
Yes, sir.
Yeah.
I am Subra Kundu. Your session is very nice. Problem collection is very important because this type of problem is so much important for net. That's why it is very effective for me. Thank you, sir. Thank you, Vinod sir, for conducting this type of session. Really nice.
Yeah, thank you, Subra.
Thank you, sir.
Yeah. Yeah, this Sonu Kumar. Yeah, dear participants, if any of you would like to share any feedback or comments, please make it now.
Good evening, sir.
Yeah. Yeah, Varada.
Sir, my name is Varada. So I've completed my BSc right now, and I'm also preparing for JAM. So all those topics that you have taken today, I felt it quite new, but still, as Archana told, your explanation and all the slides, everything, it just helped me to understand things well. So I think this is going to be helpful for me in the future. So thank you so much, sir, for this wonderful session. And thank you, Vinod, sir, for organizing this class for us.
Yeah, definitely. These topics are actually coming under the MSc level in a first course of ordinary differential equations in PG level. All these topics are there. So even though you may not be able to understand all the things, definitely you will learn it while doing your MSc and preparing for CSERnet. Yeah.
Sir, please share the PPT because PPT is
Yeah, that we will do. So Himanshu, please do share the PDF. We can share it along with the recording.
Sure, sir.
Yeah. Okay, any others? Yeah.
Sir, I'm Srishti. I'm preparing
Yeah.
for ISI MSQB and IIT JAM Maths and Economics. Your sessions are very detailed and they just help me think much more about my syllabus because we use Markov chains, Nelson-Seigel model, and many other models. So I sometimes think, how do they arrive? And after going to the proofs, I just quit. But after seeing your explanations, I have started to see the relation between the eigenvalues and the proofs and how that equation comes and other things. It motivates me to study deeper about the subjects. Thank you, sir.
Yeah, thank you, Srishti, for your feedback. So any others? Otherwise, I think we may wind up the session now. So once again, Himanshu, thank you very much for this 3 sessions on ordinary differential equations. I think by these 3 sessions, we have covered almost all the topics required for CSERnet from the ordinary differential equation part. So all these sessions, the recorded videos are available in our YouTube channel. So today's session will also be uploaded very shortly, most probably by today or tomorrow morning itself. So once again, Himanshu, thank you very much for being with Math Aspirants, and I request you to be with Math Aspirants for arranging more such sessions in future also. Thank you.
Thank you, sir. Thank you for inviting me. So one thing that I want to say to students as well, like, so sometimes like we are giving presentation and a few of them skip some slides, maybe you have missed it out. So I have written it, like I researched it a lot and then I made the presentation slides. So you can always go through that. So this will definitely help you. And about the sessions again, so like the sessions are really helpful. So if you really want to care about your exams, you are particularly about your rank. So there are a variety of questions, not in this session, in other sessions as well. So please go through it. There are many different kind of approaches as well that will definitely help you. So once again, best of luck for your exam. So just be mentally ready, and that's it from my side. So thank you, sir.
Yeah, thank you, Himanshu. Once again, for the participants, all the very best for your forthcoming exam. I'm sure that all of you will be able to crack the exam this time. Wish you all success in the exam. Okay, thank you, everyone. Bye.